Hello and welcome to the Linear Algebra recap for computer graphics, which is a part of the computer graphics course at KAUST. We will review several aspects of linear algebra on this lecture just to refresh your memory or to interpret the linear algebra from a more geometric perspective. So this will be an assortment of topics you would find throughout a linear algebra course, which is relevant for computer graphics and for dealing with various constructs from linear algebra, such as vectors and matrices, which are indispensable for computer graphics elements representations and their transformations. So let's start with the notion of determinants. Determinant is defined as a signed area between two vectors. So if you see here the determinant of A and B, which are two vectors shown in this image here, where A is here and B is here, the determinant means a signed area. Signed means it could be either positive or it could be negative. The operation of determinants is not commutative, so the determinant of AB is generally not determinant of BA, but it is the determinant of minus BA. So we can keep that in mind. The absolute value of the determinant will be then the area spanned by the two vectors and forming the parallelogram in 2D or in 3 dimensions, the parallelepiped. So if we have a 3D case, so we have here 3 independent vectors in 3D space, we will have this will give us a signed volume. Well, if these 3 vectors will not be independent, but one of them will be expressible as a linear combination of the other 2, then the signed volume will be equal to 0, and the determinant will be equal to 0 because there is no volume defined by such a determinant where one of the vectors can be expressed as a linear combination of the other 2. Further aspects are valid. If we are scaling a parallelogram, we can just scale its one side, but it also means that scaling one side is scaling the area. We can see it here on the following picture. We have first some A and B, so this side here will be now our A, and this A is now here 2A, this is 2A, and this is 3A, as you can see delineated on the right hand side. And you can see that we are scaling the side, and you will believe me that the area we have also scaled twofold, threefold, or quadruple fold in the fourth case here. So, and naturally, this holds also if we will be scaling the other vector by some constant k. Furthermore, the following is valid. If we are shearing a determinant, meaning that we are adding to the vector A certain multiplication of the vector B, then we will, geometrically, we are performing the shearing. And but we know that a parallelogram and a sort of corresponding unsheared rectangle, which corresponds to the parallelogram, have a constant area. So along this this height of our rectangle and parallelogram, if we are keeping the same length of the base, but the but the other side is changing in length, but it's also changing in the angle. As long as the height remains constant and the two sides are parallel to each other, so this one is parallel to this one, we will be having the same area. So no matter whether we are shearing in one direction or other direction, as shown here, it is the determinant will be equal to the determinant of the rectangle shown as the most left case on this small figure. Further is true, so a distributive law is true that the determinant of A and a vector which comes as a result of vectors B and C is equal to sum of the determinants of AB and AC. So we can see it here that the area of AB, the signed area of AB, is equal to this area, and the signed area of AC is equal to this area. Now the B plus C is this vector here. So, and we are not so sure whether the area is the same, but you can see that we have here this sort of a little triangle, a little bit of sliver shape, and the same one is on this side. So while in this case, from the area we would have a little bit less than on the left-hand side than in the case of AB plus AC, here we have the same more. So the distributive law here again holds. Let's have a look. How do we compute determinants? So let's write the vectors A and B in a form that they are represented in the coordinate space described by the unit vectors X and Y. So here, this is the A, this is A, this is B. And we can see that if we are now multiplying these two vectors, we will have this term here first. And here in this 2D case, we will end up with a determinant for this vector of x and x. So imagine what is a determinant of a, sorry, so this would be y. So let's say this is x and this is y. And so that they are equally sized. And now we have the signed area of x and x. So this is naturally 0 because there is no area spanned between the vector itself. So this will be equal to 0. What is the area spanned between x and y? Well, this area is, as these are unit vectors, so 1 times 1 is 1. So this is equal to 1. Therefore, here we have value 1 of this unit vector, and we know already that AB equals minus BA. So yx will be then minus 1. YY naturally, again, there is no area to be spanned, so this term will be also equal to 0. And we will end up in the term of our determinant xa times yb minus ya times xb. So if we are looking at it from the matrix perspective, so this is xa ya, and then this is xb, yb, then this one is multiplied with this one xa, yb, minus this and other diagonal, let's say. So this is the diagonal, and these are the other terms, minus ya xb. Okay. Similarly, we can calculate what is the signed volume of the ABC if we write our determinant calculation in the form of the 3 dimensions. We are here missing the plus xc x plus y b y plus, oh, not y b y c plus z c z, right? And it turns out, if we follow the same logic as in the two-dimensional case, this will be the multiplication of the various vectors will form us the determinant of the three-dimensional case. Okay. Now, the determinants can be useful, for example, for expressing the representation of a vector as a linear combination of other vectors. So let's say that we have here the vector c, which is depicted in the figure here, and then we have the vectors a, which is this length, and the vector b, which is this length. And we know that we can represent the C as a linear combination of AB with some multiplication factor AC and BC. Now, what is the BC, for example? Let's have a look at the problem again from the geometric perspective. So we can see that we have been talking before about the various aspects of these parallelograms. So this parallelogram, so I will represent it in showing the area in this way. What is this parallelogram? This parallelogram is A and BCB. BCBA is this parallelogram. And then there is another parallelogram, and I will texture it from different, as a slightly different pattern. So, here is this other parallelogram. These two parallelograms are having the same area. So this holds because we already discussed this, that no matter how much we change this angle, as long as we keep the sides parallel to each other, the opposite sides always parallel to each other, then and the height is the same, we will be having the same distance area. So if this holds, then we can also take out from this determinant the factor BC, because we know that a scaled side will be corresponding to the scaled area. So we can take it out. And if we take it out, then we have the following formula. BC is times BA A vectors is equal to CA. So if we just divide by the determinant BA, which we can calculate, BA is easy to calculate here, then we can find out the BC component. And analogously, we can calculate the AC component. So simply by using determinants, we can find out what is the linear combination of these two vectors so that we can represent the vector C. Let's discuss another construct of linear algebra, which is important for computer graphics, which are matrices. A matrix is a two-dimensional array of elements which are indexed in the following way. So if we have, let's say, 3 by 2 matrix, then we will have elements A, 1, 1, if this is a matrix A, and A, 1, 2, and A, 2, 1, A, 2, 2, A, 3, 1, A, 3, 2. So the first element, the I element, is indexing the rows, and the second element is indexing, the J is indexing the columns. We can perform various operations on matrices, such as, for example, addition. An addition is an operation where we are simply summing up the individual components. So if we will have here another matrix, so plus, let's say, B1, 1, B1, 2, B2, 1, B2, 2, B3, 1, B3, 2, then we just sum up the individual elements. So this one with this one, and so on, and this one with this one, in order to form the final matrix, which will be then A1, 1 plus B1, 1 will be one element. The very last element will be A3, 2 plus B3, 2. For the multiplication, the way how we multiply matrices is a little bit different. Generally, in multiplying matrices, we will be creating a product of a multiplication in such a way that an Pij, which is the product matrix of the multiplication of these two matrices, let's say A and B, we first, let's say, we first multiply a factors of a row with factors of a column. So for example, if I will be 1, then we first multiply the first element with the first element in both matrices, and then the second element in the first row with the first element in the second row for the B matrix, and so on. So the product is generally then coming as a multiplication of individual elements within rows and columns and summed up together, which is forming the product. The commutative rule doesn't hold, so AB is generally not equal to BA. Also, for both addition and multiplication, there are certain restrictions of which matrices can you multiply or add together. So as you can see, we need to have the same amount of elements in the rows in the first matrix as are columns in the second matrix, so that we can create a multiplication of these two matrices. What is an inverse element of a matrix? Inverse element of a matrix is that if we are multiplying the matrix with its inverse, we will end up with an identity matrix. What is an identity matrix? Identity matrix is a matrix which just contains elements of 1 on the diagonal and everywhere else it contains zeros. And also an inverse of a product of two matrices is equal to inverses of those individual matrices, a product of them, but in a reverse order. A transpose of a matrix is simply flipping the rows and columns in a matrix. So it's sort of an flipping along the diagonal. In transpose, the elements on the diagonal stay the same, and the element which will be, let's say, in the first element in the second row will become the second element in the first row, etc. So the element last row first element will become first elements first row's last element. So this is a simple operation, not as computationally expensive as inverse calculation, because it is just changing the indices. It also holds that the transpose of a product of a matrix is equal to product of two transpose matrices in a reverse order. The determinant of a matrix is equal to, so the signed area of a product or matrix of AB is equal to signed area, depending on the dimension, signed area or volume of the two matrices determinants individually and multiplied together. Now, for what is a determinant value of an inverse matrix is actually an reciprocal of a determinant of the original matrix. And the determinant of a transpose matrix is the same as the original matrix determinant. Now, we can perform various operations with matrices on vectors. So, for example, here we can see that we have multiplication of a matrix with another matrix, but it's actually a matrix which has only one column with two elements. So we can still perform the multiplication, and the multiplication here will result into a value which is xa, ya vector will be minus ya xa. So if we have a vector A which has certain x value, so let's say this is the x-axis and this is the y-axis. So if this is the vector A, then its value in x will be suddenly the minus y. So this is the y. So it will be minus y. And the y will be of value xa. So y is of value xa. Like this. So our vector, which is now calculated, is this. Let's call it a vector A prime, just for simplicity, A prime. And we can see that this vector is a rotated version of this vector. It has the same length as we can see. And actually, it's a vector which is perpendicular to our A. With this matrix multiplication, we have actually achieved a rotation of a vector. And this will become very important in the next lecture on transformations, because this is how we will be transforming points and vertices in space. So this is a so-called um, this matrix is um, an orthogonal matrix because it has both of these uh, um, basis vectors, 0, minus 1, 0, if we are looking at it as a row vectors, or 0, 1, and minus 1, 0. These two vectors are perpendicular to each other, and uh, and also are unit vectors. So they are orthonormal vectors, and they are forming a, orthonormal coordinate space, and they are forming so-called orthogonal matrix. So it's not called orthonormal matrix, which would fully express the properties, but it's called an orthogonal matrix. If we are dealing with row vector matrix multiplication, which has been done rather in the past, then we will multiply a vector, uh, pre-multiply the vector with a matrix, and we will end up in the same result. These days, the vectors are typically represented as column vectors, so this will be a more common way to see the multiplication of a matrix with a vector. Furthermore, we can see that we can use a representation of vectors and their transposed representation for performing various calculations we have already discussed before, such as, for example, the component-wise multiplication and summation, which is defined as a scalar product, dot product, can be represented in terms of vectors as an operation of multiplication of two vectors, where the A will be the transposed A vector. So the A vector will look like this: xa, ya, za, but its transpose will be a row vector. And row vector times column vector will create us this scalar product. We can also define something which is called an outer product, where we are multiplying a column vector with a row vector, and this will actually end up as a matrix. So it will not be even a vector, it will be even bigger, it will be a matrix if our transpose is the second vector in this multiplication. So here we can see how these components are then individual multiplications are then forming the individual elements. It's a multiplication of each component from each vector with another component. The full combination is represented here. With matrices, we have various types, and for example, in computer graphics, our matrices which we will be using for rotations will be orthogonal matrices, so that they are not scaling anything, for example, and they will simply just be rotating our objects around some coordinate origin. Identity matrix is a special type of matrix, which is a diagonal matrix with all elements on the diagonal equal to 1. A diagonal matrix is a matrix which has, so these are all square matrices, which we are talking about here. So the amount of rows and columns is the same. And an identity matrix would then have all the ones on the diagonal. On the diagonal matrix, we would have A, B, C, and the rest will be zeros. And the symmetric matrix will be a matrix where the transpose of the matrix is the same as the matrix itself. So we will have some values on the diagonal, and then we will have this value will be the same as this value will be the same as this value, and and this value will be the same as this value. An orthogonal matrix, as we discussed it, is a um, uh, is a matrix which has the all vectors either considered as a row vectors or column vectors. Both will be the matrix will have, once it is fulfilled for one direction, it will be also fulfilled for the other direction. It contains vectors which are linearly independent and are forming a orthogonal uh, coordinate system where each of these vectors is a vector of unit length and orthogonal to the other vectors which form this matrix. In such a case of orthogonal matrix, the transpose of an of an of the orthogonal matrix will be the inverse of the of the matrix. So we can see that that this will make our life much easier if we will be computing inverses of orthogonal matrices. For example, if we would like to perform a rotation in one direction and then perform a rotation in another direction, we will naturally just need the inverse of that original rotation matrix. But the as it fulfills that the transpose is the inverse, we will just be easily calculating the inverse operation of a particular rotation just by transposing the rotational matrix. And the orthogonal matrix is having all of the elements in the all the vectors in the orthogonal matrix are unit vectors, so their length is 1. And if we are multiplying these vectors, if we are creating a determinant of these vectors, so finding out what is the signed area or volume, then it will have to be an area of 1 because these vectors are all unit vectors. So if we are considering a determinants, we can see a matrix as a, for example, a vector, a row vector of column vectors. So this is the matrix where we have two column vectors, or we can consider it as the matrix, or actually as a transpose of that matrix, and we can see that the calculation of the determinants is the same. We can also see how we can use the determinants for calculating a plane, which point belongs to a plane. Let's say that our plane is defined by points P1, P2, P3, and then we have a point P which has the coordinates X, Y, and Z. Well, if we have these 3 points and they are forming a plane, then if our next point will be defining as will be laying on the plane, it will mean that the volume of this of two the volume of the spanned by the vectors p1, p2, and p1, p3, and p1, p will be equal to 0. So the, the determinant will be only then 0 if the point P lies in the plane spanned by the points P1, P2, P3. For any position outside the plane, we will form a volume which will be positive or negative signed volume, but it will not be equal to 0. How can we compute determinants? For determinants of the size of matrices 2 by 2 or 3 by 3, this is easy and we can calculate it without much of an effort. But for higher sized matrices, the operation is a little bit more advanced and involves computation of determinants of subsets of the larger matrix. Such as, for example, we can see here that the determinant of an 4 by 4 matrix is equal to an calculation which involves calculating determinants of 3 by 3 matrices, actually 4 of them. And after we calculate these matrices, then the determinants of these 3 by 3 matrices, then we multiply them with some corresponding elements of our 4 by 4 matrix, and then we perform we sum them up. So for example, in this following example, we have chosen that we are taking the individual elements of the second column here, and we will be using those. We take out this element, so to say, and then we are creating some corresponding elements, like for example the element 1 to corresponding element to element A12 will be AC12, which is an determinant of a matrix which has these elements, these 3 by 3 elements, except of these elements. And we can see it here. And it is signed with a particular sign, this the 3 by 3 determinant. And if we are summing up these two coordinates and the sum is an even number, then we will have a plus. And if the sign is an odd number, like in this case it is 3, then it will be a minus. So we have calculated for this element a corresponding submatrix and its determinant. This is the first term. The second term will be that we are taking this element here and we are finding a corresponding matrix. So the corresponding matrix will not include the element, the rows, the elements in the second row. So this matrix will look like this part, and then these two parts, and of course without this column. So this will be another 3 by 3 matrix, which will be forming the 2 by 2 submatrix of and its determinant, and so on until we have all the elements. So for A32, we also take the corresponding matrix and perform the determinant calculation. And for the last element, A42, we do the same. So once we are done with that, this will be the way how we calculate the determinant for the 4x4 matrix. How do we compute an inverse? An inverse of a matrix we can compute actually from these elements which we have computed before, which we were referring to, these submatrices and their determinants. If we are arranging them in the same sized matrix with the simple mnemonic help, that the element for the so the indexes will be now here will be the I and here will be the J. For the rows we will have the J, and for the columns we will have the I. So that this way we will. So this is sort of a transposed form of this of this of the original indices of the matrix. And this matrix is actually called an adjoint matrix to an A. Once again, if we want to calculate an inverse of a matrix, it's one way to do it is to calculate it from the determinant of the submatrices, which are denoted by the terms A, C, I, J, and we arrange them into a new 4x4 matrix where the indexing is in a transposed form, and then we scale this matrix with the determinant of the original A matrix. So, for example, furthermore, our matrix and determinant calculations can be used for solving a linear system. So here you can see a linear equation system where a matrix is representing the individual, the rows of a matrix are forming the, the coefficients associated with x1, x2, and x3 in each individual equation, and the b1, b2, b3 are the solutions of this equation. Now, how do we calculate the x1, x2, and x3? One way to do it is through, again, determinants, and we can do it by calculating a determinant of our matrix. So let's call this matrix and matrix A. And so this, we can find the matrix here, and the other matrix in the nominator will be the matrix A, but also formed from the solution vector. So the x1 is the first unknown variable, x2, and would correspond to the first column. So for the x1, we will be putting the b vector into the first column. If we will have, and the rest of the matrix will be the same of the A matrix. And from this we will calculate the determinant. For the x2, we will have a similar situation where we are having the matrix A, the determinant of the matrix A in the denominator, and in the numerator we will have the vector aj1 as a vector here, then the vector b, and then we will have the vector, sorry, ai1, and here we will have the vector ai3 and the determinant of it. And for the x3, we will calculate the x3 by a similar determinant where we will have the vector ai1 here. Oops, we are running out of space. So what we will be here will be the ai2, and then in the last column will be the vector b. And divided by the matrix A, determinant of it. So this is the Cramer's rule with which we can solve a linear system of linear equations, and it is one way to calculate it, not always the most efficient one, but sometimes it can be useful, as we have seen it in the case of the ray tracing on the previous lecture. Let's come to the last part of the linear algebra recap, which is dealing with decomposition of matrices. Imagine if we have a symmetric matrix. So a symmetric matrix means that the A equals A transpose. So this is our symmetric matrix, and such a symmetric matrix we can decompose into several matrices is a product of three matrices of the matrix Q, which is an orthogonal matrix, into a diagonal matrix, and into a vector matrix inverse Q, which is again an orthogonal matrix. And it is an transpose as well, because we know that for orthogonal matrices, the inverse is the transpose matrix. We also know, or kind of already feel, and we have mentioned it, that orthogonal matrices are actually rotations. So we can see here that there is a sequence of operations going on, and the operation associated with the orthogonal matrix will be rotation, and then the second operation with the D matrix, the diagonal matrix, will be scaling with each component having its own scaling factor. And then we have the inverse rotation matrix, which will be rotating the elements back. So we will sort of scale non-uniformly some object after rotation. So it's essentially a scaling along an arbitrary axis. If we, and in terms of eigenvalues and eigenvectors, this is exactly what is contained in these matrices. So the diagonal matrix, so the D matrix, will contain the eigenvalues lambdas on the diagonal, and so lambda 1, lambda 2, lambda 3, or in three-dimensional case, and the orthogonal matrix will contain 3 or 2 or 4, depending on how many dimensions we are referring to, vectors which are orthonormal to each other. So they are unit vectors and they are orthogonal to each other. Now let's have a look at the eigenvalue decomposition, how we can do it. So the eigenvalue decomposition is saying that a multiplication of a vector, post multiplication of a vector with a matrix, is essentially scaling this vector with a particular scalar value. And we can now represent this the same equation in a matrix form, where the matrix, in identity matrix, is multiplied with the lambda. So there will be lambdas on the diagonal. This will form a diagonal matrix with lambdas on the diagonal. If we put this term to the other side, we can take out the matrices, perform the arithmetic operations on the matrices, and then we can multiply with the vector A. Our vector A is in generally not a zero vector, but we can see that here this equation equals to 0. And this can only be the case when this matrix will be a singular matrix, meaning that the determinant of this matrix from uh, will be 0. So how can we calculate the determinant of such a matrix being 0? Well, we can, for example, 2 by 2 case, we can represent a matrix. So we have the matrix A equals A11, A12, A21, A22. And now we are simply subtracting from the diagonal the lambda values. And then if we have the determinant calculation, then we know that the determinant is calculated as A11 minus lambda times A22 minus lambda minus A21 times A12. And if we now multiply this term, we will end up in A11, A22, and then minus lambda times A22 minus lambda times A11 plus lambda squared. Of course, we have still here this term minus A21, A12. And if we rearrange that, we end up in a quadratic equation, which should be equal to 0. So we essentially, if this is the in the quadratic equation, the term A, this will be the term B, and this will be the term C, we are searching for the roots. And we know how to calculate the roots of a quadratic equation. It will be the minus b plus minus square root of b squared minus 4ac divided by 2a. And this way we can calculate the lambdas, and we will find out that there will be 2 lambdas because there are 2 roots, and a symmetric matrix will have a 2 real value roots of this quadratic equation, and these values will be our lambda 1 and lambda 2, our eigenvalues of our diagonal matrix. So this way, we will calculate that D is equal to lambda 1, lambda 2, and this we will use for obtaining the diagonal matrix. How can we calculate a our eigenvector out of this? For that, we can use this formula after we have obtained our lambdas. So first we enter one lambda into this equation, calculate the new matrix with this lambda, and then solve a linear system where we have the two unknowns for the both components of the two-dimensional vector A, so that our multiplication is equal to 0. And this we can do by, we will find out that actually there are infinitely many such solutions of eigenvectors, because they could be arbitrarily scaled. Therefore, we can fixate one of the components and give it some value, and then express the other component with respect to this value. And then finally, in order to have a vector which is unit vector, we normalize this vector. Afterwards, we can put in the second lambda and perform exactly the same operation to calculate the second eigenvector. So then we will have the eigenvectors calculated for both lambdas, and we will obtain the vector Q. And once we have our orthogonal matrix with orthogonal vectors, then our orthogonal matrix, then we can just simply transpose it to get the Q transposed. Well, perhaps it will be meaningful to go through an example of one calculation of the eigenvalue and eigenvector decomposition of a symmetric matrix. So let's start with a symmetric matrix which is 2, 1, 1, 1. So we can see that this matrix, this is a matrix A, we can see that this matrix is consists of two linearly independent vectors. They are also the matrix is symmetric, and we can see that it is also not a matrix which would be already an orthogonal matrix. So let's try to calculate out of this matrix the eigenvalues and eigenvectors. How should we proceed? You remember the matrix A minus lambda I would be now equals to 2 minus lambda 1, 1, 1 minus lambda. And now we need to calculate a determinant of this matrix, and this determinant of the matrix, so the determinant of A minus lambda I is equal to 2 minus lambda times 1 minus lambda minus 1. And this should be equal to 0. So if we calculate now 2 times 2 minus 2 lambda minus 1 lambda plus lambda square minus 1 should be actually equal to 0. And now if we Now look at it then. Lambda squared minus 3 lambda. 2 minus 1 is plus 1, should be equal to 0. So A is equal to 1, B is equal to minus 3, and C is equal to 1 in our quadratic equation. So if we calculate lambda 1, 2 is equal to 3 plus minus square root of b squared 9 minus 4ac minus 4 divided by 2a divided by 2. This is equal to 3 plus minus square root of 5, square root of 5 divided by 2. And this is then equal to some values which are approximately, lambda 1 is approximately equal to 2.618 and lambda 2 is equal to 0.382. Now, how do we calculate so this will be our diagonal matrix will be equal to 2.618, 0, 0, 0.382. This is our diagonal matrix. Our orthogonal matrix, how can we calculate that one? Well, we can calculate it from putting first one lambda into the equation. So 2 minus, and we are here, 2 minus lambda I, so 2 minus 2.618, 1, 1, 1 minus 2.618 is our matrix A minus lambda I for lambda 1. And this equals minus 0.618, 1, 1, and minus 1.618. This is our matrix, and with this matrix we should, if we now multiply this matrix, so minus 0.618, 1, 1, minus 1.618 times, and now for the first vector, so let's say q1 x, q1 y, sorry, let's say should be equal to 0. We said already that we will have infinitely many of such vectors. So let's say that one vector will be equal. This we will set to 1. Now for calculating the x value, we will simply then multiply. We will obtain the following equation: minus 618. 0.618 times x is plus 1 is equal to 0. So 0.618 x is equal to 1, and x is equal 1 divided 0.618. And this is approximately equal to 1.618. If we now normalize this vector Q1 will become normalized is equal to 0.8507 and minus, so this vector will be then this will be minus, this will be plus, and 0.5257 will be the first eigenvector. If we want to calculate the second eigenvector, we will simply put in the second eigenvalue, which will be the 0.32382. I will not bother you with the lengthy calculation. I will simply tell you that the second eigenvector is equal to minus 0.5257 and 0.8507. And we can see that these two are surely perpendicular to each other. And also, it just by eyeballing looks like they are fairly both unit vectors. So we have now, and we can form a matrix Q, which will be then formed by Q1 and Q2 vectors, column vectors. And then for Q transposed, we simply transpose the points, the elements out of diagonal. So this is how we calculate the eigenvalues and eigenvectors. And we essentially decompose this matrix A, which would be also a matrix which performs certain transformation, but inside this transformation, it is a scaling along an arbitrary axis. And now we know what will be the rotation matrix, so that the scaling is performed, and then the rotation matrix rotates the scaled version of the object back to by minus rotation of the previous rotation, represented by the matrix Q. We have also, for decomposition of non-symmetric matrices, so matrices which in general are not representing us an rotation and scaling and inverse rotation, we have another way of decomposing the square matrix into a set of two orthogonal matrices and one, again, matrix which is a diagonal matrix. However, for our matrix A, we cannot find the eigenvalues and eigenvectors. Therefore, we will compute the singular value decomposition. So the singular values will be placed on the diagonal matrix. And how do we calculate that? So let's have a look at the matrix M, which is actually a product of matrix A and transpose matrix A. So if we don't know these values yet, but what we know is that this equation holds. The second two terms are A and A transpose. And now if we get out of this transpose, we will see that the U S V transpose U and V transpose is equal to V S transpose, which is again S, and U transpose. So we can now, just by associative law which holds among multiplication of matrices, we can simply put together the two matrices V transpose times V, and this actually is equal to 1. It's an identity matrix, which is the result of this of a multiplication of the matrix with its transpose, because this is the inverse matrix to the transpose matrix is the inverse matrix of the orthogonal matrix. Therefore, we can simplify it into a U S squared U transpose of this matrix M. And this is very similar to Q and D and QT. So we will now be computing only that the D is the S is sort of square root of D, right? So we will need to square root the components on the diagonal to get the singular values on the diagonal. So now we can simply proceed with calculating the matrix M and getting the S and U as we know it from the previous calculation of the eigenvalues and eigenvectors. So just if we calculate now the A transpose product, so 1, 1, 0, 1 times 1, 1, 1, 0 is equal to, now let's calculate, 1 times 1 plus 1 times 1 is 2, and then 1 times 1 times 0, this is 1, and here for this row we have again 1, and for this row we have again 1. We actually end up in the same matrix A from the previous example of the eigenvalue decomposition. So we actually know what is the U and what is the S squared matrix. So the S squared matrix will be our eigenvalues. So these are so S is equal to, and now we have the 2.618, 0, 0, 0.382, and this is square root of it. If we look at what is the square root of these values, we will find out that this equals to 1.618 approximately 0, and this equals to 0.618 approximately. So we have the S, we have the U, we just need to calculate the V transpose. We can calculate it in the same way by just calculating it from the matrix N, which will then be A transpose times A matrix, and there we will just get the V out of the U matrix out of the product, and then we can calculate the vector V out of this. There is also another way how we can calculate it, and that is that we simply have uh, uh, have a look at this original equation and calculate the V based on putting the V on one side and all the product of all the other matrices on the other side. So we can try to do it, and that will mean that once again we have the A equals to U S V transpose, and out of this our V is equal to S inverse U transpose, which is inverse, and A and the whole thing transposed. So now we can calculate the S inverse is simply a reciprocal of those terms. So we have these terms, remember 1.618 is one term, and let's do, and I'll draw it nicer. So this is equal to 1.618 again. 1 divided 1.618, and then 1, 1, and 0, 0, and 1 divided 0.618 will be our S inverse matrix, and then we will have our other matrices will be the U transpose will be 0.85 approximately, and 0.52 approximately 0.52. So this is a transpose U matrix, and 0.85. Remember, these are the Q1 and Q vectors, but they are transposed. The 0.52 was previously in the second row, first column. And now the A is equal to 1101. So if we just multiply all these terms and then we transpose them, so this still needs to be transposed, then we will obtain our matrix V, which is also orthogonal, and it is therefore also representing a rotation. Well, while this is a little bit tedious and perhaps boring to calculate such a product, I will just show you the final result, which is approximately 0.52 minus 0.85, 0.85, 0.52 is the final matrix. This is the product calculation. So this also would need to be transposed in order to find out the matrix V. But in our singular value decomposition, we have the U, S, and V transpose. So, and this is equal to V, and transpose from transpose will be then equal to this matrix. So this is the actual matrix V transpose. Okay, So we have finished the singular value decomposition as the last part of our linear algebra lecture. There was a short recap on determinants, on vectors, on matrices, how we can decompose these matrices into some geometrically meaningful representations which these matrices are holding and operating on the vectors. And on the next lecture, we will be continuing talking about the application of linear algebra for transformations of elements in computer graphics. Thank you for your attention.